Sometimes when you're calculating a determinant, you'd really rather not have to go along the first row. Here's a good example of that. It's not that bad since it's only 3 by 3, but you can see going along the first row, there's going to be 3 different terms in the expansion of the determinant that we're going to have to calculate. Wouldn't it be nice if we could go along any row? Then we could go along, say, the second row, and because of those zeros, we would have much less calculation to do. Unfortunately, our definition of the determinant insists that we go along the first row, but that kind of makes you wonder, well, could we switch these rows? You know, if we could switch these rows so that the 0, 1, 0 row was on the top, that would make this determinant a lot easier to calculate. So let's see what happens when you switch rows. It turns out that if you take a matrix A and you switch 2 rows to make a new matrix B, then the determinant of those 2 matrices, they aren't quite equal, but they're negatives of each other. So proving this is actually a little bit technical, so do your best to stick with me. So to start out with, first, this result is true for switching any rows, say row I and row J, but it's actually enough to show that it's true for adjacent rows. So, you know, this original statement says we could switch any 2 rows, so, you know, we could switch these 2 rows and the determinant would be the negative, but it's enough to switch adjacent rows because if we have suppose we have some matrix where we want to switch non-adjacent rows. Okay, well, to make that happen, we can do a whole series of switching of adjacent rows. So we could start out by moving the jth row up to the ith row, like that. How many row switches will that be? Well, we're going to have to switch row J with the one before it, and then the one before that, and then the one before that, all the way until row J is up in position I, and that's J minus I swaps. And that means in this last swap, as we're swapping the J row upwards, the last swap is going to swap, right before we do the last swap, row J is now in this position next to I. But then we're going to swap the first 2 rows. So that's going to move it moves the jth row to its final position, in the ith position, but it also moves the original ith row to the I plus first position. And then we need to move it down to the jth position. Well, how many swaps is that? Well, if it took j minus I swaps to get the jth row to the ith position, it's going to take j minus I minus 1 swaps to get the I plus first position down to the jth position. So the total number of swaps here is j minus I plus j minus I minus 1, and that's 2j minus 2I minus 1 swaps total. And the key thing about this is that this is an odd number of swaps, right? Because 2j minus 2I is even, because it's divisible by 2, but it's 1 less than that. So 1 less than even is odd. So it takes an odd number of swaps. Well, if we can prove that swapping adjacent rows makes the determinant change sign, then doing an odd number of swaps will change the sign an odd number of times, but flipping the minus sign an odd number of times is the same as flipping it just once. So so that means all we need to do is prove that swapping adjacent rows changes the sign. And then this argument here will take care of the rest. So we're going to swap only adjacent rows. Well, suppose we swap, so we're going to swap I and I plus, row I and row I plus 1. And let's suppose that it's not the first row. So we're going to swap adjacent rows and not the first row. And also, right, this result is, I guess I should have said this first, this result is trivially true for 1-by-1 matrices, right? If you have a 1-by-1 matrix, there's no row switching to do, so it's impossible to switch rows. if you have a 2 by 2 matrix, so A11, A12, A21, A22, right? So the determinant of this is, let me move this whole thing down here. If we take the determinant of this 2 by 2 matrix, we get the regular, sorry, this is 1, 2. We get the regular determinant formula. So that's going to be A11, A21 minus A12 times A21. If we switch the rows, there's only, with only 2 rows, there's only one possible row switch to do, and that's switching the first and the second rows. So that's going to give you A21, A22, A11, A12, and the determinant of this row, this matrix after the row swap is, right, it's this product with a plus, so A21, A12, and then the other product with a minus, so minus A11, A22. And sure enough, these two things are negatives. So this result is true for 1 by 1, and it's also true for 2 by 2. So what we're going to do now is assume, we're going to use proof by induction here, we're going to assume that the result is true for n minus 1 by n minus 1 matrices, and we're going to show that it's true for n by n matrices. Okay. If we can prove this, then we'll be done with mathematical induction because we have our base case here and then we have the implication there. Okay. Now, so we're assuming that swapping rows in smaller matrices changes the sign of the determinant. And now we need to show that it's true for n by n matrices. So there are 2 cases. The first case is the row that we're switching. Remember, I is the row number that we're switching with its neighbor. Let's suppose that that's bigger than 1. Okay, so we aren't, the 2 rows that we're interchanging are not the first 2 rows. In that case, the determinant of B is our switched matrix. In that case, the determinant of B is, it's just using the formula for the determinant, it's the sum from k equals, let me make that j instead of k. Oh, and I shouldn't call this I. No, it's okay to call it I. So determinant of B is, so B is the matrix after switching the rows. So determinant is the sum from j equals 1 to n of, so we have to expand the determinant across the first row. So this is minus 1 to the 1 plus j times b1j times the cofactor, oh, no, not the cofactor, I've already written down the minus sign, times the minor of A in position 1j. Sorry, the minor of B. Okay. Okay, so this is the sum from j equals 1 to n of minus 1 to the 1 plus j. So B1j, well, how is the B matrix related to the A matrix? The B and the A matrix have the I and I plus first rows switched. So this B1j, this is in the first row, but that's not one of the ones that has been switched. So this is actually the same as the first row of I, so first row of A, so A1j. And now what about the B1j minor? Well, this this minor, right, this is the determinant of the rest of the matrix B after you delete the first row and the jth column. And that matrix with rows with a row and a column deleted, it does have some rows that are switched, right? Because the ith row is in here somewhere. But this is the determinant of a smaller matrix, right? That once you delete a row and a column, the remaining matrix is just n by 1, or n minus 1 by n minus 1. So it's smaller. So the determinant of it, so we've switched the ith row with the I plus first row, and since it's the smaller size, our assumption tells us that this determinant is the negative of what it was before you switched the rows. But before we switched the rows, it was the ijth minor of A, or the 1jth minor of A. Oh, and I've it's hard to talk and write at the same time. So minor, there we go. Okay, but look, now we can take this minus sign, move it all the way out front. We get the sum from j equals 1 to n of minus 1 to the 1 plus j, a 1j, and then the minor for a in position 1j. But this is exactly the negative of the determinant of A. Okay, so if the adjacent rows that we switched were not the first two rows, then we've proved our result, right? The determinant after the row switch is the negative of the determinant before the row switch. So now we need to prove that, that this is true if the row that you're switching is the first and the second row. And this is tricky. You can see ahead of time that this is going to be tricky because this first case was easy because the row switching was happening in the minor. But if we switch the first and second rows, we're switching the entries that show up in front with entries that show up in the minor. And that's going to be a lot harder to keep track of. But we can do it. So let's write out the determinant of A. So the determinant of A is, write it the usual way, it's the sum from j equals 1 to n of minus 1 to the 1 plus j times a 1j times the minor of A in the 1j position. Okay, but this minor is itself a determinant, right? That's the definition of the minor. It's the determinant of the matrix you get by removing row 1 and column j. So we can expand this even further by writing out what this determinant is. So in fact, I'm going to need, it's pretty messy, so I'm going to need some more room. So this is, let's see, it's the sum from j equals 1 to n of minus 1, 1 plus j, a 1j, and now we're going to expand this determinant. Well, in this determinant, so we need to expand this determinant across its first row, and there's sort of two cases. There are the rows before the expanded across the first row, and the columns as we go across the first row come in two cases. There are columns before the one we deleted, and then there are columns after the one we deleted. So the columns before the column we deleted, which is j, those are from 1 up to j minus 1, right? We've deleted row j, so we can't, we've deleted column j, so we can't go all the way to j. So for these columns, the expansion of the determinant is minus 1 to the 1 plus, and it's k is our column index for this, for the determinant that we're expanding for this minor. So it's 1 plus k times the matrix entry in the kth column, but the first row of this minor. Well, this minor is a determinant after we've deleted the first row, so the first row after we've deleted the first row is actually the second row, so a sub 2k times the minor of A. And, well, here we're deleting we've already deleted the first row and the jth column. Now we're also deleting the second row and the kth column. So where we've deleted, for this smaller minor, we've deleted 2 columns and 2 rows. Okay, so that takes care of this minor expansion up until the jth column. Now the jth column has been deleted, so the next one is j plus 1, and then we go all the way up to n. Now we have to be super careful about our minus signs here, because, so as we go across this first row, right, say we've deleted this one maybe, so that's j. Well, for these, the row numbers here, or the column numbers go 1, 2, 3, okay, but for this minor that we're expanding, the fourth entry, the fourth term in our expansion comes from the 5th row of the original matrix. So the exponent on our minus sign here is the row number in your expansion, which is 4, even though this was column 5 in the original matrix. So what we need here isn't 1 plus k, it's just k, right? Because this, the term we're on in our expansion is 1 less than the position we're on from our original matrix. Okay, times a2k times the minor of A in where we've deleted row 1 column j and row 2 column k. All right. Now, it's not obvious that this is a good thing to do, but we are eventually going to want this multiplied out, so let's just distribute it now. So we can distribute this big sigma on the outside. We get, so from these first 2 pieces, we get the sum from j equals 1 to n. Let's gather up our, and then inside of that, the sum from k equals 1 to j minus 1. So inside of this, we have 1 plus j factors of minus 1 here, and then another 1 plus k right here. So altogether, we have minus 1 to the power of 1 plus j plus 1 plus k, and that's 2 plus j plus k, times a1j times a2k times the minor of A, where we've deleted row 1 and column j, and row 2 and column k. Okay, now let's distribute this first outside sum all the way over to here. We get, I'm going to have to write a little smaller, sum from j equals 1 to n, and then sum from k equals j plus 1 to n. So again, this time when we gather up all our factors of minus 1, we have 1 plus j plus k. And then a1j, a2k, and the minor of A, where we've deleted row 1, column j, row 2, column k. Okay, so this whole mess, remember, is the determinant of A. Okay, now let's write down the determinant of B. Remember, B is the matrix A after we've switched the first 2 rows. Okay, so just expanding the determinant across the first row of B, we get sum from, so I know ahead of time, because I've worked this out ahead of time, that it's going to be easier to compare later if instead of using j for my first sum here, I use k. So I'm going to do that. So k is going from 1 to n, so we're expanding across the first row. So this is minus 1 to the 1 plus k, b1k minor b, where we are deleting row 1, column k. Okay, so just like before, what we're going to do is expand this minor even further, and it comes out looking exactly the same as before, except with the k's and the j's switched and b's wherever we had a's. So I'm going to skip to the end result. So sum from k equals 1 to n, sum from j equals 1 to k minus 1, minus 1 to the 2 plus j plus k, a1k times a2j, and then the minor of, I'm sorry, not a, these should be b's. b1k, b2j, the minor of b, where we've deleted row 1 column k and row 2 column j, plus sum from k equals 1 to n, sum from j equals k plus 1 to n, minus 1 to the 1 plus j plus k, b1k, b2j, and then the minor of b, where we've deleted row 1, column k, row 2, column j. Okay. Now, at this point, we can't really compare these two things because the first one is written in terms of the a's, and the second one is written in terms of the b's. But the a's and the b's are related, right? Because the matrix B is the matrix A, but with the first two rows swapped. So let's reinterpret this expression for the determinant of B in terms of the a's. So this is sum from k equals 1 to n, sum from j equals 1 to k minus 1, minus 1 to the 2 plus j plus k. So what is b1k? Well, that's the entry in B that's in row 1 and column k. But row 1 of B is row 2 of A. So b1k is a2k. And by this same token, b2j is a1j times the minor of, so now we need to figure out what is this minor in terms of A. Well, so in this minor, we've deleted row 1 and row 2 and column j and column k. But row 1 and row 2, those are the two rows that we switched. If we delete the two rows that we switched, the remaining parts of both A and B are exactly the same. So after we delete row 1 and row 2, B is the same as A, so we can write A here. So we've deleted row 1 and row 2, and we've deleted column K and column J. It doesn't matter whether we say column K and column J or column J and column K, right? Either way, we've deleted them both, so we can write J, K right here. And then the same thing for this second double sum. So sum from k equals 1 to n, sum from j equals k plus 1 to n, minus 1 to the 1 plus j plus k, times, so again, b1k, that's a2k, and b2j, that's a1j. And then we have the minor. And then this minor with B is the same thing as A because we've deleted the two rows that we switched. So deleted rows 1 and 2 and deleted columns J and K. Okay, now what is different about these two things? There are two places where they differ. So one place where they differ is that, well, the main place that they differ is that the j's and the sums, the position of the j and the k have switched in our sum, right? On this first one, j is in the first position and k is inside, and on the second one, k is inside and j is outside. Also, something, so that's where the first one differs from the last one here. But also there's an interesting difference just in each row. So this minus 1 is to the 2 plus j plus k. And over here it's 1 plus j plus k. And that seems wrong somehow. It seems like they should be the same. And we can make them be the same. We can make them be the same because if we take this sum here and multiply it out in front by -1, we can compensate for that by multiplying inside by -1 as well, because we've multiplied it by -1 twice, and so that means it hasn't actually changed. But now we can combine the -1s inside the sign, and that makes this exponent 1 plus j plus k increase by 1. So now it's 2 plus j plus k. And we can do the same thing down here. Multiply this by -1, inside by -1 as well, and that makes this a 2 instead of a 1. Okay. So let me write out the state of play. We have our first one, so the determinant of A was the sum from j equals 1 to n, sum from k equals 1 to j minus 1 of -1, 2 plus j plus k times a1j, a2k times the minor of A, where we've deleted row 1 and row 2, column j and column k. And then this minus sign here, or this -1, that we can write that, we can make that, express that as this plus being a minus. So minus the sum from j equals 1 to n, sum from k equals j plus 1 to n, -1 to the 2 plus j plus k, times, and then what do we have? a1j, a2k, and then the minor for A, where we've deleted row 1 and row 2, column j and column k. So that's the determinant of A. Now the determinant of B is this one right here. So determinant of B is the sum from k equals 1 to n, sum from j equals 1 to k minus 1. And what you'll notice is that it's actually exactly the same. Right? All of these pieces are exactly the same now. Even over here, these are the same. Right? So -1. So I'm going to write a lot of stuff down, but really I'm just copying, essentially copying the line above. So I won't say it as I write it, I guess. So these two lines look very similar, but there's an important difference between them. And the important difference between them is, right, the only difference left now is the position of k and j. And that actually makes a big difference because k in our, well, let me finish writing before I forget about what I'm doing. J is going from k plus 1 to n, and we have -1, 2 plus j plus k, a1j, a2k, and then the minor of A in the where we've removed row 1 and row 2, and column j and column k. Okay, so the different positions of the j's and the k's actually make a big difference because even though this expression inside this first sum is the same as right down here, these sigmas are talking about different j's and k's. So although this expression is the same, if we actually wrote out all of these sums, we would have different terms sitting here, right? So let's keep track of which combinations of j's and k's show up in each one of these, right? We have 4 things to keep track of. There's this one, there's this one, and there's this one, and there's this one. Right? All of these have the same expression inside of the sigmas. It's just they all have different, each sum has different combinations of j's and k's. So let's do the red one. when I say do the red one, I mean let's figure out what combination of j's and k's is this sum actually summing over. A good way to keep track of that is to sort of write it out as if it's some coordinates. So if we had, so j is going from 1 down to n, and in this sum, k is going from 1 here, so this is my k direction. K is going from 1 up to j minus 1. So in this first position, there's actually, right, when j is 1, there's no k value that's bigger than 1 and less than j minus 1. So this first sum in the red box, it doesn't get anything in this j equals 1 row. But when j is 2, then, right, when j is 2, this inside sum has a k equals 1 term. So this spot right here is part of this red sum. Okay, when j is 3, k can be 1 and 2, so it's like this. You can see we're getting this stair-step pattern, and this continues to here, right? When j is n, k can go from 1 up to j minus 1, but if j is n, j minus 1 is n minus 1. So in that case, when j is n, k goes from 1 all the way up to n minus 1. So here, right? So this red box, the sum in this red box, has all combinations of j and k in this sort of red stair-step area in my jk diagram. Okay, now let's do the, oh, and they're all counting as plus, right? Because there's a plus in front here. So now let's look at the green. So the green, j is going from 1 to n again, but this time it's going, the k's are going from j plus 1 up to n. So in this case, we actually get this side here. And there's a minus because of this minus sign out front. Okay? You can see on each row, k is starting one more than j and going up to the end, which is n. Okay, so this is sort of a picture of the determinant of, or the terms that show up in the determinant of A, and the signs that they get. Okay, now let's do the blue and the yellow. We're going to have the same sort of picture, right? J can go from 1 to n, and k can go from 1 to n. Okay, so let's do the blue. So for the blue, k can go from 1 to n, fine. So this time, since k is on the outside, we have to do things by column first. So j is going from 1 to k plus 1. So when k is 1, there aren't any numbers between 1 and k minus 1, because k minus 1 is 0. So there aren't any numbers bigger than 1 and less than 0. So nothing, we don't get anything in the first column, so for this blue piece. So how about in the second column? Well, now in the second column, k is 2, so j can be 1. So we get this spot right here. And then in the third column, we get the first two values for j, and so on. We get this same kind of stair step, like this, up to when k is n, j will go from 1 all the way up to k minus 1, which is n minus 1. So everything but the last spot. And this all is positive because there's a plus right here. Okay, now finally, let's do the yellow box. So for the yellow box, for each column, we're going from k plus 1 to n. Well, that's this stair step here. So it's all of this stuff, all of these combinations of j and k, but they all have an extra minus sign. Well, look at these two diagrams. The combinations of j and k that these two diagrams are describing are the same combinations of j and k, but anything that was negative over here is positive over here, and anything positive on the left is negative on the right. Okay, so the determinant of A is the red stuff with a plus in front of it minus the green stuff. Okay. And the determinant of B is the the blue stuff with a plus in front of it and then minus the yellow stuff. But the yellow and the red, those are the same terms, right? The only difference between them was that the yellow stuff, when we were accounting for the yellow stuff, it had a minus sign in front of it. But right, we've accounted for that minus sign. It's out here. So the red and the yellow, they're actually equal to each other, right? They're exactly the same terms. And the blue and the green are actually equal to each other for exactly the same reason. So this determinant of B, the blue, it's actually, the blue is exactly the same as the green, so the determinant of B is actually the green stuff minus the yellow stuff, but the yellow stuff is the red stuff. And you can see that these two things, red minus green and green minus red, those are negatives. So what we've finally shown is that the determinant of A is just the negative of the determinant of B, right? So to sum up, we showed that if you interchange, this was the hard case, we showed that if you interchange the first two rows, then the determinant switches sign. We also showed if you interchange any other two later adjacent rows, the determinant switches sign. So now we know if you interchange any pair of adjacent rows, the determinant changes sign. Up here, we counted up the fact that if you swap any two rows, it's actually an odd number of adjacent interchanges, and so it's an odd number of sign changes. And that means that no matter which two rows you switch, the determinant just changes sign. Now that's sort of a minor miracle. What we'll see is all of the really interesting properties about the determinant flow from this particular property. There's one property of the determinant that follows from this that is sort of immediately the nicest, which is this. Let's see what happens when we write down a determinant-like expansion, but instead of going across the first row, we go across the ith row. So to keep track of what's going on here, let's write down, so if we expand across the ith row, right, that's as if the ith row were actually up here, right? Imagine moving the ith row to the top and all the rows that were above the ith row down below it, right? Then expanding across the ith row of our original matrix A is like expanding across the first row of this matrix with the rows switched around. So that's, let's call this matrix B. So let's write down this expansion. So this is sum from j equals 1 to n, aij, and then this cofactor is minus 1 to the I plus j times the minor of A with the ith row and jth column removed. Well, let's write this in terms of B, because right, A going across the ith row of A is like going across the first row of B. So the ith, right, these aij, those are the ith row of A. So that's the first row of B, so B1j times minus 1 to the I plus j times some minor of B. But what minor of B is it? Well, if we remove the jth column from A, that's the same as removing the jth column from B, right? Because the entries of these two jth columns are in different orders, but they're the same. They're the same entries, just in a different order. So since we're deleting them both, we sort of catch all of the entries that have changed. Okay, so now let's think about what happens with the row that we're deleting. So if we delete the ith row of A, that's like deleting the first row of B. So this minor, the corresponding minor for B is 1j, right? What I'm saying here is if you delete the ith row and jth column of A, the remaining pieces are exactly the same as what you get when you delete the first row and jth column of B. Right? The remaining pieces are just all of the same entries. All of the entries that moved by this permutation that we did have been put in either deleted or put into the same spot. Okay. You can see that this expression we have written down now, it's trying to be a determinant. The only thing that makes it wrong about being a determinant is the sum of these indices here are supposed to show up on the power of I, or on the power of -1. But we can fix that. We can fix that just by, so we have I plus j in this exponent, but we're supposed to have 1 plus j because that's because those are the subscripts on our entry b1j down here. Well, that's okay. We can write this as -1 to the I minus 1 times -1 to the 1 plus j, right? If we use the law of exponents to put these back together, we would get back to where we started. So these two things are the same. Okay, times the minor of b in the 1j position. Okay. Now this -1 to the I minus j, that doesn't have, -1 to the I minus 1, that doesn't have a j in it. So we can move it, we can factor it outside of our sum like this. -1 to the I minus 1 times sum from j equals 1 to n, b1j minus 1 to the 1 plus j times the minor of b in the ij position. And this is -1 to the I minus 1 times the determinant of b. Okay, so we got this expansion that looks like a determinant but isn't because it's along the wrong row, is equal to -1 to the I minus 1 times the determinant of b. But look, if we look up at the determinant of b, how can we turn A into B by switching rows? Well, to turn A into B, we had to switch we need to move the ith row to the first row. So we can switch the ith row with the row before it, right? And then now switch it with the row before that, and the row before that, and so on. And that does exactly this permutation of rows. It takes the first I minus 1 rows and puts them down here, and it takes the ith row and it puts it first. So how many switches did we do? Well, we had to move the ith row up I minus 1 positions. So we did I minus 1 switches. Well, what we proved before is that if you switch 2 rows, it gives you a factor of -1. Right? Well, we did I minus 1 switches, so we get I minus 1 factors of -1 times the determinant of the matrix that you started with, but that was A. But -1 to the I minus 1 times -1 to the I minus 1, that's -1 to the 2i minus 2. But 2i minus 2 is even. If you raise -1 to an even power, you get 1. So this is just the determinant of A. But remember what we started with. What we started with was the sum from j equals 1 to n of aij times the cofactor of a in the ij position. So what this is saying is, look, you can get the determinant of a by expanding along any row. It doesn't have to be the first row. This is sort of one of the magical things about the determinant. It seems very surprising that expanding along any row would give you the same result, but in fact it does. Let's look at a couple examples because it's a little hard to believe. So let's find this 3 by 3 determinant. So if we didn't know what we just figured out, right? Now we know that you can expand the determinant along any row and you always get the same thing. If we didn't know that, we would expand along the first row. And this is what we'd get. So we'd get 6 times the determinant down here is 3 minus 7 times, and then the determinant here is 0 plus negative 4 from here times the determinant here, which is 0 plus 4. So 18 minus 16, so 2, right? So this particular example wasn't that bad, but it clearly would be easier if we expanded this determinant across the second row, because there are so many zeros in the second row. So if we do the determinant along the second row, we have to be a little careful about the minus signs that come from our cofactor, right? So along the first row, the minus 1 to various powers, it gave us a plus and then a minus and then a plus. But along the second row, it's a minus, a plus, and then a minus. So we have to be a little careful. So minus 0 times some determinant, right, from a minor, but who cares what this determinant is because it's times 0. And then plus 1 times, and then the determinant of, after deleting the second row and second column, which is 6 times 3, which is 18, minus negative 4 times negative 4 is positive 16. Okay, plus, and then for this last term across the second row, it's, well, I guess it's minus, but minus 0 times some determinant. But again, it's 0 times the determinant, so who cares what the determinant is? And you can see the whole thing is 2, and which is what it should be, but it was much easier to get because we were able to pick a row that had lots of zeros in it. All right. So you can see if there are zeros around, if you pick your row strategically, you can make calculating a determinant a lot easier on yourself. Let's look at another example where that happens. So let's find the determinant of a triangular matrix. So a triangular matrix, right, any square matrix has these diagonal entries, and a triangular matrix is just a matrix that is all zeros either below that diagonal, like the matrix A, or above that diagonal, like this matrix B. So A here is called upper triangular, and B is called lower triangular. Upper and lower triangular matrices have some nice properties in general, but for now I just want to calculate their determinant. So let's calculate the determinant of A. Actually, let's do B first. For B, where are the most zeros? Well, the row with the most zeros is the first row, because in the first row, only the first entry is non-zero. So everything, since this is lower triangular, everything above the diagonal is 0, so this is all zeros in this first row. So if we go across the first row, we get, if we expand across the first row, we get B11 times the determinant of, right now we throw out the first row and the first column and find the determinant of the square that's left. So the upper left corner of this square is B22. Okay, so times the determinant of that smaller matrix from B22 to BNN. Okay, but look, this smaller matrix is also upper triangular. It has zeros above the diagonal. So let's expand this smaller determinant across its first row. So we get B11 times B22 times a yet smaller determinant. But, you know, every time we do this, we're getting a square that is all zeros above the diagonal, so we can just go across the first row. And you can see every time we do this, we just pick up one more of the diagonal entries. So when we're all done, it's B11 times B22 and so on. Right, this is all times, not plus. So B22 times B33 all the way up to BNN. Right? And the key thing is, right, all the other terms of the determinant that you get from finishing all your expansions, they all start with 0 times something. And it doesn't really matter what that something is because it's getting multiplied by 0. So for a lower triangular matrix, the determinant is just the product of the diagonal entries. That's a really nice result. What about upper triangular matrices? Well, you can see if we had to work out a determinant across the first row, finding the determinant of this upper triangular matrix would be a pain because we'd get a bunch of terms because each of these entries across the first row could be non-zero. But now we know you don't have to expand across the first row. You could expand across any row. So let's choose the row with the most zeros. Let's do the last row. So the determinant of A is, right, only the very last, right, most terms in this determinant start with 0 times something. The only term in the expansion that doesn't have a 0 in front of it is the last one. So that's the only one that survives. So ANN times the determinant of this smaller piece. But this smaller piece, it has all zeros in the last row except for the last entry, which is A sub n minus 1, n minus 1. And so we can expand this smaller determinant across the last row, and we just only pick up one term, and it has a n minus 1, n minus 1. And, you know, the same thing is happening here as happened with the upper triangular case. So we just get the product of all of the diagonal entries again. Right? So for upper and lower triangular matrices, the determinant is just the product of the diagonal entries. One last result here is, let's find the determinant of a matrix with a row of zeros. Well, it doesn't matter where that row of zeros is. So here's our matrix with the row of zeros. It doesn't matter where that row of zeros is. If you expand across the row that is all zeros, you just get 0 for the determinant because every term in the expansion starts with 0 times something else. So it's all 0. All right, so you can see being able to expand matrices across, or being able to expand determinants across any rows is really handy when it comes to calculating determinants for many important cases. We'll see later that it actually lets us do a lot more than that. So this fact about determinants turns out to be incredibly important.